Hey everyone, it's your boy Trail. Today we'd like to look at creating this plant stand in a procedural manner. So the challenge that I had when creating this was I needed larger and smaller plant stands for certain areas of the scene that I was laying out. So with that, I needed to create this in a procedural way. And the difficulty was getting these connection areas at this inclined angle and how I would do that in a procedural manner. So I set about doing that. So let's look at how I accomplish that. I'm sure there are different ways how you could do this, but I'm going to look at the way that I chose to go about this and that brought me satisfactory results. So first we start off with the legs. And for the leg, of course, it's just a box. And then my group, we'll see what this group is about in a minute. And then the transformation, this is just to rotate the box a little bit to get those angles correct at normals, then do a copy. Now we can look at so this is copied at a 120 angle because of course it is a triangle. So now we can look at the group. So this group I call the group main face group. So you can see I'm really just grouping these interfaces where the braces will connect. So that's what that group is for. This extract centroid SOP. What this basically does, what I'm doing here is I have it set to run over the primitives, and I'm transferring the normal attribute. Now, this normal here, this normal node here, should take a closer look at this because I'm creating normals on the primitive, right? So I'm making sure that I have primitive normals because we'll use this later on. So here, when I do the extraction, I'm doing it on primitives and I'm telling that I want to output points. And here it's asking me what attributes do I want to transfer from that primitive onto the points. And I'm saying I want to transfer the normals. And I also want to transfer the main face group, okay? So we do that, and you can see if I should select points and look at the main face group, you can see, again, we're selecting those points that were generated from the main face group. So the group is being transferred, and also the normals. You can see that the normals are coming over as we would expect. So then we do a blast because we're only interested in these main, and that's why we transferred over that group, because we're only interested in these points that come off the main face group. So we blast and delete everything else. Okay, so we only have these points remaining. Then we do this transform SOP here just to basically move these points up and down. We'll see that later on. It's not crucial to the setup. It's crucial to the procedural nature, but not to the way how the setup works. So we can move on from that. So before we move on to this copy to point SOP, what this SOP is doing, by the way, is just copying on the braces. So before we move on, let's look at how we are creating those braces. So again, first we start with a box, then we do a transform to line this up with the z-axis so that it gets copied onto our points in the right way. And then we're doing a group SOP. Here we're grouping the faces that will be connected, the face that will be connected exactly on where the points are located. So the points that we'll be copying onto, they are, and the face that will be copied exactly to those point positions, we're grouping that particular face. That's what we're doing here, right? Then immediately we're converting that group into an edge group. And this is very important. We'll come back and look at that later, why we converted this into an edge group. And we can see here in the group promote SOP, we have it set to include only elements on the boundary. If we don't turn that on, we could end up getting into problems where we get these edges included into our group, and we don't want that. So turn on include only elements on the boundary. Okay, so now we're getting the correct group that we want. Then we add some normals. These normals that we're adding are primitive normals. So you can see that this is what we're adding. We're adding the primitive normals. We then do a attribute promote to change this from primitive normals to point normals. And we're using the last match method. And I'll show you why we choose to use the last match method. So let's look at the primitive normals. You can see we have normals going along the Z, we have normals going along the X, and we have normals going along the Y. But when we transfer these onto our points, we want the normals going along the X axis. Those are the normals that we want to get transferred over to our point. So you can see if we choose first match, this is what we'll get. We'll get those normals that are going along the Y axis. We don't want that. So last match gives us exactly what we want. And we'll see in a moment why we need these normals in a later part of our setup. So now we do the copy to points. Let's turn these normals off so that they're not too distracting. And here we can see with the copy to points, another thing that I want you to keep in mind is that the length of these braces are also important because we'll be doing a ray intersection. And if the length of any one of these braces is too short, then the ray will not hit anything and we won't get the correct result that we're looking for. So these braces need to be long enough to ensure that they cross the path of our ray. And if you don't know what I'm talking about, we'll see that in a moment where we do the ray intersection calculations. So after this copy to points, we're doing this convert line, right? So here where we created this group where we converted this primitive group into an edge group. Here is where we're now using that edge group in this convert line SOP. So essentially what the convert line SOP does is it takes, if we should remove the group, what it does, you can see, so this was our original geometry, pass it through the convert line SOP, and what that does is it takes our polygonal edges and basically turns them into polygonal curves, essentially. But because we only want these faces, we only want these edges in our result, so that's why we're using the group. That's why we're using the group here, so that we only get those faces, and also make sure that you remove unused points, because if you don't remove unused points, you can see this is what our results will look like. So be sure to remove unused points. Now we move on to this attribute wrangle. Essentially what this attribute wrangle is doing, as you can see here, it says this wrangle calculates correct direction vectors and then ensures that they all point in the same direction using the dot product technique. So let's take a look at this. The reason why we're doing this calculation here inside this wrangle is because we want to ensure that all of these faces are pointing in the same direction, which is inward. We want to make sure that the normals are pointing inward from all the faces. So let's look at what happens when we create this directional vector. So this yellow vector is our directional vector. Let's shorten the length so that we can see this better. Okay, so this is our direction vectors. You can see some are pointing inwards and some are pointing outwards. We don't want that. We want them all to be pointing inwards. So that's what this wrangle essentially does at the end here. I have it commented out at the moment, so we'll look at it in a minute to see how it fixes that. But first, let's look at how we calculate this directional vector in the first place. So we're creating an arbitrary up vector and we're using the normal. So we're using this arbitrary up vector and our point normals. So remember when we did this attribute promotion here to get these point normals that are going along the x-axis, those are the point normals that we're now using within this wrangle to do our directional vector calculations. So let's turn off the directional vector for a moment. So we're doing a cross product between the normals here, and this arbitrary up vector that we have, which is just an up vector going in the y. So just imagine a vector going up in the y. As a matter of fact, let's just create an up vector attribute here just for reference. So now let's turn this on. And let's make this green, bright green. Okay, so this is our up vector. So this is exactly what our up vector looks like. So now we have the normals and our up vector, and we're doing a cross product between the normals and the up vector. Now, remember the cross product, if we should take a look at this drawing that I have in Photoshop here, the cross product will always give us a vector that's orthogonal to both of the vectors that we use in the cross product calculation. So you can see here, I say if we do a cross product of vectors A and B, that always gives us a third vector, which is orthogonal to both A and B. Orthogonal just means 90 degrees. So we're at a 90-degree angle. So if we do the normal and the y, right? So imagine that this blue axis is the normal and this green is the up vector, and we do a cross product between that, we will end up getting this red vector, this x-axis. That's what the cross product will give us. So in our case, what the cross product here will actually give us is this directional vector. Okay, so let's turn this directional vector on, and this is what we'll get. So a cross product between the normal and the up will end up giving us this directional vector here. But because some normals are going in the left direction, some normals are going in the right direction, what happened is that the resulting directional vector could either be going inwards or it could be pointing outwards. We want to ensure that all of our directional vectors are pointing inwards. So here, so when we do this normalization, right? When we do this cross product calculation, to create the directional vector in the first place, we then now need to figure out some logic to check if those vectors are pointing inwards or outward. And here's where we start to do that. So what we do first is we get the positional vector. So to think about position in the way that we're using it here, what we're actually looking at is the point position, right? So we're looking at the point position, and the point position is calculated from the origin, from the 0 position in the world. Right? So what we are getting with every point position is a vector that's going from the origin to that point position. So we have a vector going from here to here, right? So we do the negative. We want the normalized negative of that vector, of that positional vector, which will now give us a vector that's going from the point position to the origin. So we now have a vector going from the point position to the origin. Okay, and that's what we want. So we're going to check against that vector. So what the dot product will essentially tell us, if we jump back to this Photoshop drawing here, what this dot product will actually tell us, if we take a look at it here, we see the dot product can tell us if two vectors are pointing in the same direction. The value returned is scalar. If the value is above 0, the vectors are pointing more than less in the same direction. If the value is less than 0, then the vectors are pointing more or less in the opposite direction. And if the value is 0, then the vectors are orthogonal to each other. And just remember, orthogonal simply means 90 degrees to each other. So again, let's jump back into Houdini. And now we can see why we would do this dot product here. So we're doing a dot product between the directional vector and basically the reversed positional vector, essentially, because instead of having a vector going from the origin to the point positions, we have a vector going from the point positions to the origin. So we're doing a check with the dot product to see if our directional vector is pointing roughly in the same direction as vectors which would be pointing from the point to the position, which is inside. So if a vector is pointing from the point position to the origin, it's going in the direction that we want. So we're doing a check here to say, is the directional vector pointing in the same direction as our reversed point position direction, essentially? So then here we're using this conditional statement to make the check. So we're saying if that result is less than or equal to 0, which means that they are not pointing in the same direction, then we want to basically reverse those normals. So to reverse the normals is just simply multiplication by -1. So if it's not pointing in the same direction, do a multiplication by -1 and reverse those directional vectors. And that's essentially what happens here. So now we have all the vectors pointing in the same direction, which is exactly what we want. Then we just do an attribute swap because, I don't know, for some reason I prefer to have this directional vector in the normals. So I did a swap and change it from the directional vector attribute into the normals. That's what this swap here does, you can see. And then we do an attribute delete to delete the directional vector attribute because we no longer need it because we now have it in our normals. And also we do not need this up vector here because I just created that so that you could better see what's going on, right? So now we have our directional vectors, right, which we place into our normals. And now we can move on into this somewhat complicated looking for each block here, but it's very simple, to be honest. This connectivity swap is just creating a primitive class attribute on our primitives, right? We also should take a look at what we have happening over here in this branch because it's important. So remember when we originally copied our braces here, we just created a separate network here where we created some normals, regular vertex normals, and then we also did a connectivity swap where we created a primitive class attribute, just like we did here, right? So we'll see how those two play with each other in a minute. Okay, now before jumping into the for each block, we should probably try to explain what it does before we jump into it because there's a little bit going on that I think we should try to explain first. So we mentioned this chain over here where we're just taking the braces that were initially copied, adding some typical normals, and then doing a connectivity to create a class attribute. Let's take a closer look at this class attribute because it's important that we understand why we created both these class attributes, both on the curve primitives here and also on these primitives that will eventually become our collision geometry. So I have a visualizer here for the class attribute, and you can see again, it's an integer attribute, so it just creates a number, and all the primitives have the exact same for each brace. All the primitive have the exact same number, the exact same class attribute. So you can see for this primitive, for this geometry, all the primitives have a class attribute of 0. So 0 for this face, 0 for this face, 0 for this face, 0 for this face, and so on. This one is 1, and this one is 2. So we have a class attribute with 3 unique values, 0, 1, and 2. Now let's look at our curve primitives here. We have the same thing. We have class attribute. Again, each curve, each geometry have the same class attribute. So for this one, it's 0, for this one, it's 1, and for this one, it's 2. Now let's template our braces here, and look at our curve geometry. Now, remember, so let's focus on this one. Let's focus on this brace piece right here. It has a class attribute of 2, okay? Has a class attribute of 2, remember that. So this one, class attribute of 2, and now we're looking at this curve geometry here, and it has a class attribute of 1. So this curve geometry with a class attribute of 1, we want it to collide with this brace geometry with a class attribute of 2, okay? So remember, has a class attribute of 2. So we want this geometry with a class attribute of 1 to collide with this geometry with a class attribute of 2. And the same goes for all these other pieces. So for example, this curve geometry has a class attribute of 2, and we want it to collide with this geometry here, which has a class attribute of 0. So we want this has a class attribute of 0. This has a class attribute of 2. So we want the one with a class attribute of 2 to collide with this here, which has a class attribute of 0. And the same again goes for the other piece. So just remember that. That's what this setup in here is all about. So now we can hopefully that made sense, and we can now jump into the for each block. So we're looking at this. Let's untemplate this. So now we're operating on each of these individually. Let's change the background to dark so that we can better see what we're doing here. Okay, so let's see if I can change the color of that class attribute. Change it to light green maybe, and go large. Okay, so we can see better. All right, now also again, before we continue in this loop, we should also talk about this IntersectAll vex function. So let's bring up that in the documentation so we can take a look at that. So here it says the IntersectAll function, it computes all intersections of the specified ray with the geometry, and we can look at the arguments that this function takes. So first, the geometry, you can give it a group. It takes the origin. So the origin is, as you can see here, you can read here what all of these arguments are. So the orig is the ray origin point. For us, the ray origin point is going to be the center. Okay, it's going to be the center of this geometry, which is why we have this extract centroid sub here, which gives us that centroid, and we store it as a detail attribute. And here within the wrangle, you can see we immediately import this centroid, and it will be, so you have centroid, it's our ray origin point, as you can see here. So let's jump back to the documentation. Okay, takes a dir, which is a direction. So ray direction and maximum distance. This function does not expect a normalized directional vector. Instead, it uses the length of the vector as the maximum distance to search. Okay, so the length of your vector basically determines how far out the ray will go to find a collision geometry, to find a geometry to intersect with. And you can see here we have this position array, which here you see it says the function overrides this array with the world positions of each hit. So anywhere array hits on an external geometry, it will store those. So if it hits multiple geometry, it would store. That's why this is an array, because this can potentially. That's why the function is called IntersectAll, because it can hit more than one surface. So if it hits more than one surface, it needs an array to store each position, each hit position. So that's why this is an array, okay? And it does the same for the primitive. So it stores the number of the faces that were hit, the faces that were intersected with. It stores those numbers in this primitive attribute, and it does the same for UVs. So it stores the UV coordinates of that hit location also in this vector. And here it also I didn't use any of these. Okay, so we can skip over those. You can check this out on your own time. So, and you can see what this function returns. It returns the number of intersections are 0 if the ray didn't hit anything. So we're not really interested at the moment in what this returns. We're more interested in what it gives us in these attributes that it will override. So in our wrangle, that's why we have these attributes here, the hit pos, UVW, and the hit prim. So we're using them in the IntersectAll, right? So our hit positions, it will store all our hit positions in this variable. It will store all our hit prim numbers in this variable, and it will store the UV locations of all those hits in this variable. Okay, and then we have the direction that we want to search in, the ray direction, and we have the centroid. So notice our ray direction, we're just importing our normals. Remember when we did this attribute swap up here to get our directional vector into our normal? So this is what we're using. Okay, this is what we're using. This is our ray direction. Hopefully that makes sense. So we have the ray direction, we have the centroid, which is our ray origin. We should actually call this ray orig, just so that it kind of matches more closely with what we see in the documentation, so that there's no confusion. So again, if we look at the documentation, we see orig, okay, the ray origin point. So that's our centroid. Okay, for the Prim group, let's look at this section here. First, before we look at that section, notice that the IntersectAll, notice that the geometry that we're giving it is coming in on not the first input, not input 0, but input 1, which is the second input of our wrangle. And notice that again is our collision primitives. We're calling these, let's drop down a null, and we're calling these our collision primitives. And this kind of naming is really coming from I'm using the terminology from our RACEOP because the RACEOP calls this the collision primitives. So, or it has a parameter called the collision group. So I'm kind of just stealing that terminology and calling this the collision primitives. So let's turn off the normals for a minute. So again, remember this has the class attribute, and our curve primitives also have a class attribute. So remember, we already spoke about how we're using these class attributes to ensure that the right curve geometry collides with the right primitive from this chain when we do the intersect. Okay, so notice that this is coming in on the second port of our wrangle, and that's what we're doing the ray intersection against. So we're saying that if the ray from our current geometry, this normal, if this ray intersects with anything that's coming in from our second port, which is this, so the ray from this going that way, going this way. So here it is, the ray. So if a ray coming that way intersects, which it will, okay, it will intersect. So you see, this is the geometry that we're looking at, and the ray is going in the right direction, so it will intersect. So keep that in mind. Definitely keep that in mind. So now again, let's jump back to looking at the Prim group. Also, let's jump to the documentation and look at what it says about the Prim group. It says, if given, only intersects primitives in this group. Okay, if given, and we have given it. So let's look at how we're determining what's inside of that Prim group. This is using the class. This is just creating the logic for the class collisions that we explained earlier between these two chains. So here we're saying that, so we're creating this empty Prim group variable, this empty string variable, which we will fill with one of these string values depending on what the value of the class attribute on the Prim that we're running over is. So currently we're running over this Prim, and the class attribute is 2. Okay, so notice we're importing that class attribute here. Again, it's an integer attribute, and we're importing it into this variable called class val. So we're importing this Prim class attribute into this variable called the class val. So now let's look at this bit of the code here, because again, we're running over this Prim and its class attribute is 2. So let's just look at the condition that says what happens if that class attribute is 2. So if that class attribute is 2, we're saying fill this Prim group variable. So replace it from being an empty variable and now make it become this string, which says a class equals to 0. So if our class value is 2, then Prim group should equal the string at class equals 0. And keep in mind that this is a string. So don't be fooled by the at class thing that we're creating an attribute here. This is a string. All of this is a string, and we're creating this string and storing it in this Prim group variable. Now, that's what this Prim group now evaluates to. For this, because we're in the loop now, we're running over this particular primitive, this Prim group now evaluates to at class equals 0. Now, how does this work? How does passing that on as the Prim group work? Because remember, this is the collision prims that we are currently running over, all right? And remember that it has a class attribute. So let's turn off these normals. So remember, it has the class attribute, and we can see, because we have the visualizer on here for class, we can see these numbers, okay? So remember, again, if the value is equal to 2, which now it is because we're running over this primitive, and this class value is equal to 2, what our Prim group will evaluate to is at class equals 0. So now again, let's look at this, and we have a class attribute here on this primitive, which is equal to 0, all right? Now again, this is our curve geometry with its class equal to 2, the one that we're currently running over in this for each block equal to 2, and here is our geometry with its class equal to 0, and we want to collide with it. We want this one with 2 to collide only this one with its class attribute of 0, which is exactly what's happening here again. So we're setting the group. So this again is what we call an ad hoc group. So we're setting it on the fly. We're setting this group on the fly to be equal to. So it's essentially like having a group SOP, right? So let's create a group SOP and connect this geometry. Okay, you can see everything is grouped. So let's turn off that, turn off the base group. So now nothing is grouped. There's no group. See, there's no group. Group 3 equals 0. There's nothing within it. Now, if we should say, bring back the base group. And if we should say at class equals 0, okay? This is what we get. So now it's grouping only this geometry where its class attribute equals to 0. Okay, so this is essentially what we're doing here inside the wrangle. When we say make the primitive group a string value of @class equals 0, and then we're passing it to the IntersectAll function as our group. And remember, we're operating on the geometry that's coming in on our second input, which is our collision geometry here. So essentially, that's doing the same thing as grouping, as how we group this using that. It's doing the same thing here, but we're doing it inside the wrangle just to ensure that this primitive that we're currently running over only intersects with this collision primitive with its class value of 0. So that's what we're doing. And the rest of the code, the rest of what's happening here is just doing that exact same thing, but for the different primitives. So if the primitive has a class attribute equal to 1, it will look at this bit of the condition right here, which is saying class value equal 1, then set prim group to @class equals 2, which would essentially be the same thing as changing this to, already change it to 2. All right. So you can see if we look here, prim, the class value of 1, okay, and come here, we want it to collide this prim here with a class attribute of 2. So hopefully that makes sense. Hopefully it makes sense, the explanation of how we're using these logic to determine our collision prim, right? So if it doesn't, please leave some comments and I'll try to do a clearer explanation. Please tell me what it is that you didn't understand and I'll try to make it clearer. All right, so that's our ray intersect. Now this bit of code here, please read the comments. This is saying we use this attribute later in the ray sub to determine our collision group. So here we're creating an attribute, right? We're creating a detail attribute. The attribute is called collision prim. You can look up the set detail attribute function in the docs, but it takes the geometry and it takes the name of the attribute. Here we're calling it collision prim, and it takes the value that we want to set that attribute to. Here we want to set it to the hit prim number. Now remember, the hit prim is an array, and remember that we pass it to the IntersectAll function so that it can be replaced with the primitives, the face number of the primitives that were hit within the intersect when it did the intersect. But because we know that only one face was hit, we only want the first element because we know only the first element exists in this array. So we say hit prims give us element 0, which will equate to the face number of the prim that was hit from this collision branch over here, right? And notice we say that we use it later in the ray sub. So let's look at the ray sub. Again, template our collision geometry and look at what the ray sub gives us. Template this from here and see, now we're actually getting the ray done and we're getting that collision. All right, so let's look at how we use this attribute inside of the ray sub. So we use it here to determine notice this is a collision group and it says group of primitives to project on. And we know we only want to project on. To also notice that what's coming in on the second input of this ray sub is our same collision geometry. And back to this group here, we know we only want to collide with the primitives that were hit in our intersect check here, which is why we're putting that number into this detail attribute. And we're using a detail attribute because we just want that attribute once. We want it we want all the primitives to look at that one attribute. Okay, so we're putting it into the detail attribute, and what it evaluates to is the face number of the primitive that was hit. In this case, we know that face number here, this face right here, this face, which is face 4, we can't see it because it's hidden by this geometry, but we know. Oh, sorry. Let me turn on face numbers. Let's turn off the class. Let's turn on face numbers, and it is hidden by that geometry, but trust me, it is this face right here. It's face number 4. There you can see it. There you go. It's face number 4. Okay, so that's what this evaluates to. It evaluates to 4. And so we're only projecting onto this face, which is face number 4. And we're getting exactly what we want. All right. So after this, it is pretty much smooth sailing after this. So we have our original curve, and we now have our curve, which has now been rayed onto our collision prim, and we run them both through a polypath sop just to make sure that they're both a closed curve, so they're connected. And then we merge them. We do a merge here, and then we just do a skin sop to create the actual geometry between them. So if we should template now our legs, get back to our legs geometry, template those, see what we have. All right, so we have our skin. We do a fuse to make sure that it's all fused up, but you can see, we can still see right through that it's not capped. So we run it through a clean sop just to make sure all the polygons are oriented the right way, fix any overlaps. All right, delete any overlapping pairs of geometry. We don't know what kind of geometry. We want to make sure geometry is clean. And then we do the polyfill, okay? Just fill these faces. All right, and essentially, before I run through the rest of this loop, because there are some interesting things going on here, so I will run through it. But before I do that, let's just look at the result. You can see it does that for all of these braces, and we end up with exactly what we want. In this branch over here, we just have the legs coming in, and all we're doing is adding some noise to the legs. I have it turned off here because we're using VDBs to actually do that, and the VDBs slow down the calculation, so I just turned them off. But I can turn them back on here, so you can see that all we're doing to the legs here, this whole loop, this whole for each block on the legs, is just adding this bit of noise to it. So you can see just adding these noise that's going along the vertical direction of the wood. Okay, so if I should turn back off this, see, no noise. That's all it's doing. So we get to that in a moment. And by the way, that's all the rest of this the rest of these nodes in this for each block for the braces. That's all it's doing as well, just adding some noise. So if I should again turn off these, you'll see that we get some noise. Give it a second to calculate. Again, you'll see that all it's doing is adding some noise, this time along the horizontal of the wood, because I'm saying that this is the grain direction, essentially. So I'm going to save the rest of the tutorial where I'll explain how I handled the noise, because that's essentially what the rest of it is about, how I handled creating the noise pattern and ensuring that it runs in the correct direction along the grain of the wood, both for these braces and for the legs. It's the same technique, and it's interesting. It's just some simple vector math stuff, but I think it's interesting to show. So again, I'll save that for a part 2 of this tutorial because I think this is a bit long. So thank you for watching. It's your boy Trail. Definitely like and subscribe, and I'll see you later.